Okay, we're recording now. Okay, so let me go ahead and share my screen just to show you guys what is in Schoology. Okay, on today, we are continuing our conversation into energy. Okay, so remember last class period, we went over some concepts with energy, and we're going to kind of expand on that on today. So if you click on the 4th period class, go to materials, fit 6 weeks. Okay. Today is April the 14th. For B Day, it will be April the 15th. And of course, today is a Wednesday. Okay. So on today, we're going to go over the conservation of energy PowerPoint. There are a few example problems on this PowerPoint that we're going to work out together as a class. So I'm going to need for you guys to have some sort of calculator next to you, because you guys are going to help me out with these computations. And then as soon as we get done going over all those example problems, I am going to open up the assignment in Schoology titled Conservation of Energy. Okay, so that is the goal for today. Okay. Excuse me, guys. I know I'm feeling sleepy. Okay, so briefly, let me remind you guys of what we talked about last time. So let me go ahead and open up that PowerPoint from last time in Kami so that I can discuss a few things. Okay, so if you remember on last time, we started out talking about gravitational potential energy. And just to remind you guys what gravitational potential energy is. It's the energy that an object has as a result of its height above the surface of the earth. So this ball here, I'm holding it above the surface of the earth, right? So it's above the ground, and there's a gravitational field surrounding the object. So as I take this object and I release it, the object's going to accelerate. So because the object accelerates, in other words, it moves, I know that the very fact of me holding this object above the surface of the earth supplies the object with potential energy. In other words, it stores energy within this ball. That stored energy is what is referred to as gravitational potential energy. And I just need for you guys to remember the equation for gravitational potential energy is equal to the object's mass times 9.8 times height. Where it's understood in this equation right here that little g is equal to 9.8. Okay. So that is the equation for gravitational potential energy. Okay. We also talked about kinetic energy. Remember, an object's kinetic energy is due to the object's motion. So kinetic energy is equal to 1/2 times the object's mass times its velocity squared. Okay. So this is the mathematical equation for kinetic energy. 1/2 times mass times velocity squared. Any object that's in motion has kinetic energy, which obviously means any object at rest has no kinetic energy. And of course, another thing that we talked about elastic potential energy. So remember, guys, anytime you have an object that can either stretch or compress, you can supply that object with elastic potential energy. In this case, this rubber band here. Guys, the very fact of me stretching the rubber band stores energy within this object. So there's stored energy in the object as a function of me stretching it. Okay, so that stored energy is what is referred to as elastic potential energy. And guys, the equation for elastic potential energy, let me write this down. The equation for elastic potential energy is equal to 1/2 times k times x squared. Okay. So, and of course, it's understood in this equation here, k is what is known as our spring constant. This number here, or the number that goes here, just basically refers to the stiffness of the material that you're working with. So different types of materials have different stiffness values. They have different spring constants. Another way you can think about it, is that you can think about this number as being a representative of the elasticity of the material. Okay, so that's what K is. K just means the magnitude of stiffness. X in this equation refers to the distance stretched or compressed. So if I take my object here, and let's say I stretch it 0.2 meters. So if I stretch my object 0.2 meters, then I will plug that in for X. X refers to the distance stretched or compressed. So, and this is the equation for elastic potential energy. And on your homework assignment for today, this equation you're not going to have to use that much. I believe there's like one question on the assignment where you have to use the elastic potential energy equation. All of the other questions on the assignment basically involves gravitational potential energy or kinetic energy. So we don't use this equation that much, but we do use it at times in this class. Okay, now, with that said, one of the things that I talked about last time is I gave you guys this example of showing you guys how potential energy can be converted to kinetic energy back into potential energy, and so on. And I want you guys to see this here. So here, notice how we have this guy here at a skate park, and so he's kind of just going up this ramp. So if you guys notice, when he's at his highest point, he has his greatest potential energy, right? Because he's above the surface of the earth. So here he has his greatest gravitational potential energy. And at the very bottom, he has his greatest kinetic energy. In other words, he's moving his fastest at that point. So notice how, energy keeps converting back and forward, back and forward, back and forward. And again, the assumption is here there is no friction to dampen the system. So the guy or our system, he just keeps going. So you just keep seeing that potential energy becomes kinetic energy, back into potential energy, and then it just keeps going. It just keeps moving like that, and so on. Okay. Now, on today, I want to go over this conservation of energy PowerPoint. And I put this PowerPoint in Schoology. So we're going to go over this. There will be a few problems at the end of this PowerPoint that we're going to do together as a class. But first, let's start off with going over the concepts. Okay, so conservation of energy. The law of conservation of energy states that energy is never created nor destroyed, just transformed into other forms of energy. Okay, so guys, please remember this. It turns out that the total energy in the universe remains conserved. In other words, it remains constant. Guys, it is not possible to add energy to the universe or take away energy from the universe. The total energy that exists in the universe is, and it's all that will ever be. Okay, energy is neither created nor destroyed, just transformed. And we kind of see an example of this here. Notice how in this system right here, notice how energy just keeps transforming from, in this case, kinetic energy to potential energy, back to kinetic energy, and then back to potential energy. So notice how energy just keeps transforming. Energy can change forms, but the total energy stays constant. Okay. That's what the law of conservation of energy says, that the total energy for the entire universe stays conserved. In other words, it stays constant. Now, I want you guys to consider this here. Imagine in this particular situation right here, imagine that I did have friction involved in this particular situation. So imagine there was friction between the ramp and the skater. Well, guys, it should be obvious to you guys that if there was friction between the ramp and the skater, eventually this guy would slow down, and eventually come to a stop here at the very bottom, right? So if there was friction, he would kind of slow down a little bit, oscillate, and then he would come to a stop. So at the moment that he comes to a stop, he has no potential energy or kinetic energy. So he has neither. So guys, let me ask you a question. Did I violate the law of conservation of energy here? Did I take energy out of the universe by slowing this guy to a stop? What do y'all think? Yes or no? If he slowed to a stop, did I violate the conservation of energy principle here?
No.
No, I did not. So now it turns out that we might have lost kinetic energy, we might have lost potential energy, but I promise you guys that energy was transformed into something else. Because remember what I said, friction stops the skater. So because friction is involved, what type of energy was created here? I want you guys to think about this. So guys, if you take your hands and you rub them together, notice there's friction between your two hands. What type of friction are you? What type of energy are you creating in this situation? Anyone want to tell me in the chat box?
Thermal.
I heard it.
Thermal.
Thermal, exactly. Thermal energy. Yeah. Thank you, Stephanie. Thank you, Angelina. Yes, I am creating thermal energy. So the point is, guys, even though friction brought this guy to a stop and he lost kinetic energy and he lost gravitational potential energy, I promise you that he did pick up some thermal energy, but the thermal energy was basically created in the molecules along this ramp. Okay. So the point is, the total energy in the universe can never be lost. It can just be transformed into different forms. And of course, you guys experience that whenever you rub your hands together. Notice as you rub your hands together, they get hotter because you are creating heat. Okay, you're creating heat. You're creating thermal energy. Okay, because there's friction between your two hands. But the point is, the total energy remains conserved. Okay. Now, now in this case right here, guys, if we ignored friction, and again, this animation right here is assuming we're ignoring friction. Okay, if we ignore friction, um, he just keeps going. In other words, gravitational potential energy becomes kinetic energy, becomes gravitational potential energy, and so on. Okay. Now, um, let me ask you guys a question. If Let us assume this skateboarder here. Let us assume that while he's at the very top of his path, let us assume that he has um, 50 joules of potential energy at the very top of his path. So at the very top, he has 50 joules of potential energy. Can someone tell me how many joules of kinetic energy will he have when he reaches the very bottom here? Anyone? Tell me in the chat box. So in this particular example here, how many joules of kinetic energy will we have at the very bottom? Come on, guys. If he has 50 joules of potential energy at the very top, yes, Stephanie, by the time he reaches the bottom here, all of that potential energy was converted into kinetic energy, right? So if he started out with 50 joules of potential energy, then he must have 50 joules of kinetic energy. Because remember what I said, and energy is conserved. Energy stays the same, right? We are ignoring friction here. Since we're ignoring friction here, all of that potential energy gets converted into kinetic energy. Someone tell me, guys, when he reaches the halfway point, so when he reaches his halfway point, assuming he's exactly halfway, how many joules of potential energy do you guys think he will have at this point? Guys, at the halfway mark, yes, Stephanie, he would have 25 joules of potential energy. Yeah, so he would have 25 joules of potential energy. How many joules of kinetic energy will he have? also 25 joules. Exactly. So y'all see that? So again, the assumption is like at this halfway point right here. So at the halfway point, when he's at half of his original height, he has 25 joules of potential energy and he has 25 joules of kinetic energy. And that makes sense though, because the total energy has to add up to 50. Okay, right? Because remember, the total energy has to stay the same. Okay. And of course, when he's at this point right here, he has 50 joules of potential energy. Okay. And notice when he reaches this point right here, all of that potential energy gets converted to kinetic energy. So now he has 50 joules of kinetic energy. And then back at this point right here, he has 50 joules of potential energy. Okay, so you guys get the point. So, with that said, guys, let me write down the most basic equation that you guys are going to use for your assignment. Let me write this down now, because this is the most important thing. So, according to what we just saw, basically, you guys have just seen that whatever, hold on, basically, you guys have just seen that whatever the object's potential energy is at the very top of its path is equal to the object's kinetic energy at the bottom of its path. Okay. So if I were you guys, I would write this down, because this is the most important principle you guys are going to be utilizing whenever you guys are working on your assignment later on. The object's potential energy at the top of its path is equal to the object's kinetic energy at the bottom of its path. And of course, in this in all these situations, guys, we're assuming we're ignoring friction, we're ignoring air resistance, we're ignoring all of those things. So it's basically true that the potential energy at the top of the path is going to equal to the kinetic energy at the bottom of the path. Okay. And we clearly see this here. We clearly see here that the potential energy at the top of the path is equal to the kinetic energy at the bottom of the path. Okay. So this is the most important principle that you guys are utilizing whenever you're working on your assignment. Okay. So for the remainder of the class period, we're just going to be working out some examples together. Okay. So I'm going to be working out examples from this PowerPoint in Schoology. Please be sure you have a calculator out, because I want you guys to walk. You guys are going to walk me through some of these problems. Okay, so let's start with this very first example here. This very first example says a 40-kilogram object falls freely for a distance of 15 meters near the Earth's surface. What is the kinetic energy of the object the moment just before it strikes the Earth's surface? Okay. Now, guys, we already know our equations for kinetic energy, which is equal to 1/2 times mass times velocity squared. We also know our equations for gravitational potential energy, which is equal to mass times 9.8 times height. So we already know that. And this question right here says, what is the kinetic energy of the object the moment just before it strikes the Earth? Now, guys, if you look at this equation here, in order to calculate kinetic energy, we are going to need to know the object's velocity. Like, if we wanted to use this equation, we would need to know that. However, if you look, they don't give us the velocity anywhere in the problem. So we just can't use the kinetic energy equation here. But I want you guys to look at what they do give us. They give us the object's mass, and they give us the height, which is 15 meters. So in other words, they give us all the information to calculate the object's potential energy. But guys, remember what I just said. If we know potential energy at the very top, then we know that the kinetic energy at the bottom has to be numerically equal to that. So let me just write this down. So let me zoom in here. So potential energy at the top is equal to kinetic energy at the bottom. Now, we can easily calculate the potential energy at the top because the equation for potential energy is mass times 9.8 times height. Once we know that, that'll tell us what our kinetic energy is at the very bottom. So notice the mass is 40 kilograms. Little g is always 9.8. And the height here is 15. Can someone put that in your calculator and tell me what you guys get for the kinetic energy? Thank you, Stephanie. So that means by the time we reach the very bottom here, this person has 5,880 joules of kinetic energy. So that's how we do that first one. And of course, we were able to solve that because notice notice how we were able to solve that is because they gave us all the information to calculate the potential energy at the top, which since we know the potential energy at the top, we were easily able to find the kinetic energy at the bottom. Angelina, you're good? Did you see how Stephanie found that? She just did 40 times 9.8 times 15. Okay, awesome.
Oh, so that's the equation to solve for kinetic energy?
Yeah, yes. Yeah, we just used that principle here. Yeah, because look, Jeremiah, they gave us the information to solve for potential energy at the top, right? But since we know what the potential energy is at the top, then we also know what the kinetic energy is at the bottom. So yes, that's how we were able to solve for kinetic energy. Make sense?
So you said they gave you the potential energy at the top?
They gave you the information to calculate the potential energy at the top. They gave you mass and height. So even though we couldn't calculate kinetic energy, we could calculate potential energy. But according to this principle here, Jeremiah, if you know one, you know the other. That's the basic idea.
Okay.
Mm-hmm. All right, Jeremiah. As we do more problems, it'll click. It'll make more sense as we go through more examples.
All right.
All right. Okay. So let's look at this one right here. This problem right here. This problem right here says a 6-kilogram ball is thrown into the air with an initial kinetic energy of 75 joules. Approximately how high will the ball rise? Okay. So guys, notice what they give us. They tell us the moment the ball was released. So if you take a ball and you throw it upward, they tell us right at the moment that it was released, it had it had 75 joules of kinetic energy. So in other words, they told us what the kinetic energy of the object is at the very bottom of its path. So guess what? That is going to enable us to solve for the heights at the very top. So with that said, let us use this principle here. Potential energy at the very top is equal to the kinetic energy at the very bottom. So let me write that down. Potential energy at the very top is equal to kinetic energy at the very bottom. Okay. Now, guys, let us fill in what we know. They tell us that the initial kinetic energy was 75 joules. So in other words, at the very bottom of its path, we're going to plug in 75 joules for kinetic energy. Okay, so that was given, guys. They tell us we had 75 joules of kinetic energy the moment that ball was thrown upward. Okay. Now, guys, as this ball is thrown upward, it's obviously going to gain potential energy, right? So it's going to gain some potential energy, and we know the equation for potential energy is mass times 9.8 times height. Okay. So if we know that the object's potential energy is going to equal to 75 joules at the very top, guess what? We can easily solve this equation for height by plugging in what we know. So we know the mass is 6 kilograms. Little g is 9.8. Again, our goal is to solve this equation for height. All of that is equal to 75 joules. Okay. So let's simplify this further, guys. So if you take 9.8 and multiply by 6, what you get, you get 58.6 1.8, all of that multiplied by h, all of that is equal to 75. Can someone tell me, how do I solve this equation for h, for the height?
You need to get h by itself.
And how do I do that?
Gotta divide.
Exactly. Thank you, sir. And can someone tell me what y'all get when y'all did that? Thank you, Iman. So yes, Iman said that the height is 1.28 meters. Iman, that's exactly what I got on my worksheet. Meters. So that's what I got for h. Any questions there? Right, because the problem says approximately how high will the ball rise. So all we did here was solve for h. Awesome. Okay, can I move on? Just trying to make sure I'm not moving too fast. Okay, I'm going to move on. I think you guys are good. Let's move on to this next one here. In this next problem right here, it says a 55-kilogram object is thrown into the air and it reaches a maximum height of 30 meters. Calculate the kinetic energy of the object the moment it was released. Okay, so guys, so notice that, so in this case right here, we take an object and we throw it upward. So in this case, kinetic energy was transformed into potential energy, right? Because it says it reached a maximum height of 30 meters. So whatever its potential energy is at the top must be equal to its kinetic energy at the bottom. Now, they don't give us any velocity or anything here, so they don't give us enough information to use the 1/2 mv squared equation, but they do give us enough information to tell us how much potential energy the object has once it reaches the top of its path. So they do give us mass and they do give us height. So guess what? We can just plug everything in to this equation here, and that'll tell us what the kinetic energy the object has the moment it was released at the bottom of its path. So its mass was 55, little g is always 9.8, and the height was 30 meters. Can someone tell me how much kinetic energy this object has the moment it was released? Yes, Angelina, that is what I got. So my kinetic energy, and I'll write off to the side here, is equal to joules. Right? So energy is always in joules. Okay. Any questions there? All right, guys, we have about 4 more we're going to do. I want to do it just enough so that you guys understand how to do the homework assignment. I'll do different. Okay. So if you look at this one right here, so this problem right here says an 80-kilogram object is going 45 meters per second at the bottom of the hill. Calculate the potential energy at the top of the hill. Okay. So guys, if we haven't, so guys, so in this case right here, we have a situation in which an object starts out moving at the bottom of the hill at 45 meters per second, and then it rolls upward and slows down and reaches the very top. And we want to know how much potential energy it has at the very top of the hill. Okay, so let's write down our principle here. Potential energy at the very top is going to equal to kinetic energy at the very bottom. Okay. Now, they don't give us a height here, so they don't give us enough information to calculate potential energy directly. But guess what? They do give us enough information to calculate kinetic energy. Okay? And guys, y'all know the equation for kinetic energy is 1/2 times mass times velocity squared. So basically, if we plug everything into our equation, 1/2 times mass times velocity squared, that will immediately tell us what our potential energy is at the very top. Okay. So let's just plug everything in. So 1/2, guys, remember that's the same thing as 0.5. We're told our mass is 80 kilograms, and we know that our velocity is 45. So can someone tell me what 0.5 times 80 times 45 squared is? Because once we know that, we'll know what the potential energy is. Yes. Hold on. No, Stephanie, that's not what I got. Yeah, that's right, Angelina. It's actually the potential energy would be what Angelina said, 81,000 joules. Don't forget the square. the 45. Thank you, Angelina. 81,000 joules. All right, guys. We just got 3 more. Okay. So look at this one right here. It says a 10-kilogram object strikes the ground with 7,500 joules of kinetic energy after falling freely from rest. How far above the ground was the object released? Okay, guys. So, guys, if you take an object here and you drop it from some height, what we know is by the time this object reached the very bottom of its path, it had 7,500 joules of kinetic energy. Christine, is that what you needed? Okay. So now, guys, when the object strikes the ground, it has 7,500 joules of kinetic energy. So we want to know how far was it released. So remember, just use our basic principle that we've been discussing. Potential energy at the top is equal to kinetic energy at the bottom. Okay. So, guys, we know that the moment this object was released, we know that it was released we know that when it was released, by the time it hit the bottom, it had 7,500 joules of kinetic energy. Okay, all right, so I'm taking this number here and I'm plugging it in here because that's what we're told. We have 7,500 joules of kinetic energy. Our goal is to find out the height the object was released from, because it says how far above the ground was the object dropped. We know our equation for potential energy is mgh. So guys, our goal is to plug everything in and to solve this equation for height. So we know our mass is 10 kilograms. Little g is always 9.8. And our goal is to solve this equation for height. So all of this is equal to 7,500 joules. Okay. Now, guys, y'all should know 10 times 9.8 is equal to 98. 98 times h is equal to 7,500 joules. Can someone solve that equation for H and tell me what you guys got for that? Yes, definitely. That's exactly what I got for my height. Thank you, ma'am. So my height here was 76.53. And guys, remember your units. Your units are in meters, right? Because you're solving for height. Okay. Hopefully that makes sense to everyone. Okay, guys, we got two more, and then we're gonna call it a day. Look at this one right here. This says a 3 kilogram object is thrown into the air going 60 meters per second. How high does it go? Okay. So guys, so if I take an object and I throw it upward, and so it starts off with some initial kinetic energy, and it's going to go up, and gains potential energy, and it's going to go to some height. Now, what I'm going to do, I'm going to work this problem out on another sheet of paper because I don't have enough room on this PowerPoint here to work out two problems. So let me work this out here. So remember, guys, using our principle that the potential energy at the top is equal to the kinetic energy at the bottom. So, guys, before I can figure out how high it goes, the very first thing I need to know, I need to figure out how many joules of kinetic energy did it have when it was released. In order to figure that out, I'm going to use this equation 1/2 times mass times velocity squared. Right? Because obviously, if I know that, that's going to enable me to solve for the potential energy at the top, which is going to be helpful in a moment. So let's plug in what we know. We know the mass is 3 kilograms, so let's plug that in. 0.5 times 3 kilograms. Notice, guys, the velocity is 60 meters per second. So, guys, I'm going to take 0.5 times 3 times 60 squared. When I do that, I get, for my potential energy, I get, yes, thank you, Angelina, 5,400 joules of kinetic energy. Okay. But guys, notice I'm not done here because notice what the problem says. It says, how high does it go? So I know that whatever this kinetic energy is at the bottom has to be equal to this potential energy at the top. So meaning I can just use my MGH equation, set that equal to 5,400, and solve this equation for height. So let's just plug everything in. The mass is 3 kilograms. Little g is always 9.8. Now it's up to you guys to solve this equation for height. Three times 9.8, that's guys, whenever y'all solve this equation for height, what do y'all get? Guys, what do y'all get? Yes, thank you, Angelina. That's exactly what I got. So my height here, where it says how high does this go? My height here was 183.67. And again, height is in meters, guys. So your units has to always be correct. Height is in meters. Any questions on that one before we do this last one? All right. Let me go ahead and clear this screen here so I have enough room to write for my last one. Okay, so this last one right here, I'm going to do, it says a 3-kilogram mass at rest on the ground is pushed by an 8-Newton force and goes a vertical distance of 4 meters. How fast is the mass going immediately after it was released? Guys, in some of these problems, they're going to give you extra information. Like, for example, we don't need to know the magnitude of the force that this object was pushed with, because that's not really important to the problem. There's no force in those equations. The key thing is what we need to know is the object was pushed from rest. So like you kind of imagine you're taking a ball and taking a ball and pushing it upward, okay, or throwing it upward. As long as you know that it has a 3-kilogram mass, and the moment it was released from the hand, it went a total distance of 4 meters. You can easily calculate how fast the mass was going after it was released. Easily, okay. So, in other words, guys, when it says how fast, we're solving this equation for velocity. Now, remember what I said. Whatever the object's kinetic energy is at the bottom has to be numerically equal to its potential energy at the top. Okay, so the object goes a total distance of 4 meters. So mgh. So that's I'm going to use this equation here to figure out how much kinetic energy it had. So mgh is equal to ke. So we know the mass was 3 kilograms. Little g is always 9.8. And it tells us that the height, that it went a total of 4 meters. So that was its vertical distance. That was the height that it went. So guys, if I put that in my calculator, if I put 3 times 9.8 times 4 in my calculator, what I get 117.6 joules of potential energy. And obviously, guys, it should be obvious to you guys that is going to that potential energy at the top is going to equal to the kinetic energy that it had while it was at the bottom. Okay. Now, we're not done because remember what it says. We want to solve this equation for velocity. So, like, guys, I'm gonna write this down. Y'all remember the equation for kinetic energy is 1/2 times mass times velocity squared. So all of that gets equal to 117.6 joules. Okay. Now, guys, let us just plug in what we know. We know the mass is 3 kilograms. So I'm going to plug in mass into this equation here. So 117.6 equals 0.5 times 3 times velocity squared. Okay. Follow me so far? Now, what you guys have to do is you have to get velocity by itself. Okay. So, guys, 0.5 times 3, that is the same thing as 1.5. Okay. So let's keep going. Remember, our ultimate goal is to solve this equation for V. Okay. And guys, y'all know this is basic algebra here. I need to divide by 1.5. That goes away. Whatever do to one side, I have to do to the other. So if I take 117.6 and divide that by 1.5, I get 78.4 is equal to v squared. And lastly, guys, y'all tell me, how do I get rid of that squared? Thank you, Angelina. Take the square root. Okay. Yep. Thank you, Stephanie. I was just about to ask it. So Stephanie said for her velocity, she got 8.85 meters per second. So I always put your units right, 8.85 meters per second. So that's how fast the ball was moving, or the object was moving. The moment it was, it was pushed by that force. The moment it was released and started traveling upward, that's how fast it was moving. That was its velocity. Anybody want me to zoom out here so y'all can see the whole thing? Okay. You're welcome, Angelina. Okay. Any final questions for me? Okay, let me go back to Schoology. I'm going to make the assignment available to you guys. Okay, so you guys should be able to see the assignment in Schoology. And again, if you understand the principles we did today, everyone should be fine. Guys, if you have not filled out the attendance form, please do so before you leave. Guys, if there are no immediate questions for me at the moment, you guys are free to go.